All right, Chapter 3, Neets, Mile 8. Magnetic amplifiers. You have now been shown various ways with electron tube to Needs Module 6 transistors. Meets Module 7 can be used to amplify signals. You also have been shown the way in which these is done. The other type of the amplifier, and there's another type of the amplifier, you have the magnetic amplifier, sometimes called the mag amp. Magnetic amplifier has certain advantages over the other type of the amplifiers. This includes one, high efficiency up to 90%, two, the reliability, long life, freedom of the maintenance, reduction of spare parts and inventory, and three, the rugged shock, vibration, resistance, high overload capacity, or high overload capability, freedom of the effects of moisture. Four, no warm-up time. The magnetic amplifier has no moving parts and can be hermetically sealed within a case similar to the conventional dry-type transformer. However, the magnetic amplifier has few disadvantages. For example, it cannot hold low level of signals. It is not useful. The frequency, the time delay associated with the magnetic effect of the output wave is not exact reproduction input wave form, poor fidelity. Magnetic amplifier is important, however, too many of the naval engineering because it provides a rugged, trouble-free device. Has many applications aboard a ship and aircraft. The applications include throttle control of the main engine, shift the speed, the frequency, voltage, current, and the temperature control of the auxiliary equipment, fire control, servo mechanism, stabilizers of the guns, radar, and sonar equipment. As stated earlier, magnetic amplifier does not amplify magnetism, but uses electromagnetism to amplify a signal. The power amplifier limited frequency response. Technically, it falls in the classification of audio amplifier, but since the frequency response is normally limited to 100 hertz or below, magnetic amplifier is more correctly called low frequency amplifier. Basic principle of the magnetic amplifier is very simple. Remember that all amplifiers, current control devices, magnetic amplifiers use the change inductance to control power delivered in the load. Basic operation of a magnetic amplifier. Figure 329 shows a simple circuit variable inductor in series with a resistor representing a load. The voltage source of 100 volts at 60 hertz. Alright, so the 100 volts at 60 hertz, you have 1025 Henrys, variable inductor, and resistor at 5 ohms. Okay, so what happened to the inductance of the end of the result power load, the true power increase of the while looking for the formula to see how they affect the decrease of the inductancy. Inductance reductance is equal to 2 times the frequency times the load, or the impedance is equal to the inductive reactancy squared times the ohms squared, or amps is equal to the voltage over the impedance. Therefore, the true power of the amps is squared. True power is equal to amps squared over ohms. The true power of the Neets Module 2 Introduction Alternating Circuit Transformers Inductancy L decrease of the inductance capacity as the inductance capacity decreases, impedance decreases as the impedance decreases, ampage increases, finally ampage increases, the true power increases. The general conclusion can be confirmed that using some actual volt value of the inductance of formulas along with other values of the 329 and values inductance with 23 millihenries, the formula yield the following: inductive capacity is equal to 2 times the frequency times the load, or 2 times 3.14 times 60 hertz times 23 millihenries at 8.67 ohms rounded off. So therefore your impedance is equal to 8.67 ohms squared times 5 ohms squared equal to 100.1689 ohms rooted, or 10 rounded off. Impedance, your amps is equal to volts, 100 volts over 10 ohms equal to 10 amps. The true power is equal to 10 amps squared over times the ohms, or 5 amps, or 500 watts. No, the value of inductance decreased to 11.7 millihenries. Formulas yield the following values: 2 inductance, 2 times the pi times 5 frequency 60 hertz times load of 117 millihenries, or 4.41 ohms rounded off. Impedance is equal to 4.41 ohms squared times 5 ohms squared equal to 44.4481 ohms squared, or 6.67 ohms rounded off. Therefore, 100 volts is equal over 6.67 ohms is equal to 1 amps of 15 amps rounded off. True power amps is 15 amps squared times the ohms, 1125 watts. So decrease the inductance 11.3 millihenries, 23 millihenries to 11.7 millihenries. Cover the increase of power load. The true power of 625 watts, 11,225 watts minus 500 watts. It took the 1 watt of power to change the inductancy. 11.3 millihenry. Some electrical mechanical means. Figure 329 would represent a power amplifier of the gain of 625. Alright, method of changing inductancy. Since changing the inductancy coil enables the control power of the load within the massive available to change the inductancy, before answering the question, you should recall a few things for the magnetism inductor for the Neets, Module 7, introduction of the matter energy, direct current, Chapter 1, matter energy, electricity, Module 2, introduction to alternating current with the transformer, Chapter 2, inductancy. Permeability was defined measure of the ability of material to act as a path with additional magnetic lines of force. Soft iron was presented with a having high permeability compared with the air. In fact, with the permeability magnetized iron with 5,000, while air was permeability 1, not magnetized piece of the iron has high permeability because of the tiny molecule. Magnus Weber's theory of the other directions, electronic spin domain theory, are able to be aligned with by a magnetic field. As they align, they act as a path for the magnetic lines of force. Earlier, Neat model stated the inductance of the coil increased the direct of the permeability of the core material, increased the coil winding around the iron core. Permeability of the core 5,000. Is 5,000. Now if the iron is pulled apart with the coil of the wire, the core is apart from part iron and part air. Permeability of the core decrease the permeability of the core, decrease the inductancy of the coil, decrease the increase of the power delivered to the load. True power relationship is shown in Figure 330. The system shown in Figure 330 is now not too practical, even though the motor were replaced in the hand is shown. The resulting amplifier would large and expensive and not easily controlled. If the permeable core could be changed, electrical means rather than mechanical, more particular system would be result. Alright, shows the decreased permeability, decreasing inductance, power increasing from resistant load 115 volts AC. High permeability depends on being many of the molecular magnets electric expand the direction that can be aligned with the provided path of magnetic lines of force. That also allow all these available paths are already being used. Material is magnetized and there are no more paths with additional lines of force. Flux density, number of lines of force passing through a given area as high as it can be. This means the permeability material has decreased. When the condition is reached, the core is said to be saturated because of the saturated field with the magnetic lines of force it can be has. At this point, the core has also the same value of the permeability. Air is instead of the much higher value of the permeability of 5,000 has it been unmagnetized. Of course, permeability does not suddenly change from 5,000 to 1. Permeability changes the magnetic force changes until saturation reaches. Saturation permeability remains very low now, no matter how much magnetic force is increased. If you were to draw a graph of flux density compared to magnetic force, you would find that something similar to the graph shown in Figure 331. Figure 331 also includes a curve representing the value of permeability maximizing force increase point S. Figure 331 point of saturation. Flux density does not increase above point of saturation, and the permeability is steady and low value. Alright, Figure 331 shows magnetizing permeability point S saturation, magnetism curve, permeability curve, flux density. You have now seen the change of the magnetic force coupled with the change of the permeability. The next question is, how do you change the magnetic force? Magnetizing force is a function of the amperes term, the amplitude term of the magneto movement motive force developed in 1 ampere of current flowing in the coil of 1 turn. The increase of the amplitude term of the coil with the magnetic force, increase of the distance of the not practical to increase the term of the turns. The easiest way to accomplish the increase of the current of the coil, the increase of the current of the coil, increase of the amplitude term of the increase of the amplitude to increase the magnetic force at some point. This covers the decrease of the permeability of the core, the permeability of the core, decrease of the inductance of the coil, decrease, as said before, the decrease of the inductancy called the increase of the power through the load. The device that even the arrangement is called saturable core reactor, saturable core, saturable reactor. Or saturatable core reactor. Saturatable core reactor is a magnetic core reactor whose reactance is controlled by changing permeability of the core. Permeability of the core is changed by varying an unidirectional flux or in one direction through the core. Figure 320 shows there's a saturatable core reactor used for the control of the intensity of the lamp. Note that the two coils wound around the single core. The coil on the left is controlled by the rheostat and the battery. The coil is called the control coil because of its power with the control circuit. The coil on the right is connected to the lamp load, the AC source. The coil is called the load coil because of the power of the load circuit. As the wiper, the move of the connection of the rheostat is moved from the toward the right and is left. The resistance of the control circuit with the load resistant control circuit current is increased. The cause of the amount of the magnetism to cover the increase. The inductance of the core load increase. The decrease because of the core is common to both cold with less inductive load current circuits, and the load current increase the lamp that gets brighter. Figure 332 shows a simple saturated core reactor. Shows the rheostat, the voltage source, and the battery around the laminated core and the load circuit on the other poles with the AC source to the lamp. Schematic diagram shown in Figure 333 is the inductor 1 is a schematic symbol for the saturated core reactor. The core winding has 5 loops, and load winding is shown with 3 loops. Double bar between the 2 indicators from the iron core with the symbol cuts across the 2 windings and saturatable symbol indicating 2 windings for a share of the saturatable core. Alright, resistor 1, a DC source, AC source, DS1. Now you have basic operation saturatable reactor. There's only one other idea before moving one circuitry onto the circuitry of magnetic amplifier. This is the point of magnetism magnetizing the core where the suitability cores should be operated. The ideal operation point is the place in which the small increase of the control react current is a large increase of the output power. The small decrease of the current control will cause a large decrease in output power. The point of the last portion of the permittable curve after its peak. Figure 334 shows the magnetism permittability curve of the saturatable core reactor with the ideal operation point O, indicating a point O magnetism curve of the portion of the magnetism core curve, and point O is located within the knee of the curve. The knee of the curve is the point of the maximum curvature that is called the knee because it looks like a knee of the leg that is bent. Saturatable core reactor magnetic amplifier should be operated with the knee of the magnetism core. Alright, show the density, the point A, the knee, and permittable curve. When the saturatable curve is knee with the magnetism curve, the all small increase of the control current, they will cover a large increase of the load current. Small decrease of the control current will cover the large decrease in the load current. This is why point O is the ideal point for the pointing out, because of the small change of the control current will cover the large change of the load current. In other words, saturatable core reactor can amplify the control current. However, the saturatable core reactor is not a magnetic amplifier. You will find only a little later on magnetic amplifier different than saturatable core reactor. For this, first you should know that a few more things about saturatable core reactors. And DC voltage applied with the control winding of the saturatable core reactor. AC voltage is applied with load winding. The AC flux is aided with the DC flux in one half cycle, opposite with the DC flux on the other half of the cycle. This is shown in Figure 335. The load flux indicated with the dashed lines, arrows. The control flux indicates the solid lines. In View A, show the load control flux adding during the one half cycle of the AC. View B, show the figure showed load current flux opposing during other half cycle of the AC. So your AC is going left, your counterclockwise control DC, rheostat, load circuit, flux path, saturatable core flux opposing, going the clockwise from DC circuit to AC circuit. The situation covered the operating of the saturatable core reactor. The shift they applied to AC, however, the situation would be better if the load flux was not an influence of the control flux. Figure 336 showed the a circuit this is accomplished. During the first half cycle load circuit flux, dash line arrows cancel the center leg of the core. The shown Figure 336 View A, with the result of it has no effect of the flux from the control circuit during the second half cycle of the polarity of AC. Therefore, the polarity of the flux reverses is shown View B. The result of the same during the first half cycle. There is no effect upon the circuit. Control circuit flux. So you have your AC source in the middle, first half cycle load, DC in the middle, DC AC on the outside, control circuit rheostat, load, a resistor on the AC, three-legged saturatable core first half cycle. Three-legged saturatable core reactor second half cycle. Load DC in the middle, AC, rheostat. Another approach to solving the problem load flux affecting the control flux shown in Figure 337. The Figure 337 shows a toroidal saturatable core reactor. Shames of these cores are toroidal donut shaped. The windings are wound around the cores, the load flux line, and control flux in one core output of the control flux of the other core. During the first half cycle, the flux A with the left core with the opposing right core is shown in the figure 337 of view A. During the second half cycle, the flux opposing the left core adds to the right core shown in view B. Regardless of the amount of the load flux, polarity, load voltage, there is no effect of load flux on the control flux. First half cycle AC DC control circuit in the middle, fluxing aid, fluxing opposing, fluxing aid, reverse, second half cycle. Figure 336 and 337 both represent practical, workable, saturatable core reactors. Current and similar with actually the control, lightning, audiometers, electrical industrial furnaces. These circuits are sometimes referred to as magnetic amplifiers, but there is no technical correct. Magnetic amplifiers differ from the saturatable core reactor in one important aspect. Magnetic amplifier with the rectifier additional saturated core reactor. Alright, simplified magnetic amplifier circuitry. A saturatable core reactor works. Why do you need to add a rectifier to produce the magnetic amplifier? To answer this question, recall the Neets Module 2 introduction of the alternating current with the transformer. You were told high hysteresis loss. Hysteresis loss occurs between both because the AC is applied with the coil of the tiny molecular magnet's electrospinning direction to realign with the polarity of the AC chain with the realigning. The up power, the power is the realigning the loss for the rest of the circuit concerned. Because of the hysteresis loss of the saturatable core reactor, the power rests in circuit the concern because of the hysteresis loss of the saturatable core reactor, the power is gained with relatively low. A rectifier added with the low circuit is eliminating the hysteresis loss. The increase of the gain because of the rectifier allows the current to flow with the one direction through the load coils. A simple half-wave magnetic amplifier shown in figure 338 with a half-wave magnetic amplifier because of the half-wave rectifier during the half-wave cycle. Overload voltage of the diode inductive load winding develop load flux shown in view A. The dashed lines are arrows, thus the load flux of the two load coils can cancel, but they have no effect for the control flux. During the second half of the cycle, the diode has no conducting load coils developing in flux shown in figure view B. The load flux never has a reverse direction. It does the saturated core reactor, so hysteresis is eliminated. Figure 338 shows a simple half-wave magnetic amplifier first half cycle, AC source, DC cycle, control rectifier load. A simple half-wave magnetic second half cycle, control rectifier load, AC source, DC rheostat, center tap. Center core. Circuit shown in figure 338 is only able for the half load voltage, therefore the half of the possible load power with the diode blocks is control current during the half load voltage cycle. The full wave rectifier is in play for the control rectifier would allow the current to flow with the entire cycle of load voltage while still preventing hysteresis loss. Figure 3039 shows the simple full-wave magnetic amplifier. The bridge circuit of the control rectifier 1, 2, 3, and 4 allows the current to flow with the load circuit during the entire load voltage cycle. The load current is always in the same direction. Current flow with the direction prevents hysteresis loss. View A shows during the half cycle load voltage current flow with the current control rectifier load with the coils control rectifier 1 and 3. Views B show during the second half cycle with the load current rectifier 2 and the load coils the current rectifier 4. Alright, 339 show the simple full wave first half cycle. Simple full wave magnetic second half cycle. That's on your AC. Using the point control circuit, magnetic amplifier has shown with the DC applied to the magnetic amplifier control circuit that should accept the AC input signals as well as DC input signals as shown. Either figure 334 is a saturated core reactor that has an ideal operating point. Some of the DC must also apply with the saturatable core of the operating point of the DC, called the bias. The most effective way to apply the bias saturatable core also allows the AC input signal to control magnetic amplifier is to the bias winding. A full wave magnetic amplifier will the bias winding is shown in figure 340. 340 shows a full wave magnetic amplifier bias winding. Notice you have the bias winding on the DC circuit, the control loading circuit wrapped on the center tap with the control input, and your rectifier full wave rectifier, all four continuous rectifiers, AC input. In this circuit shown in figure 340, the bias circuit is adjusted to set the saturated core reactor with the ideal operation point. Input signals representing the AC source symbol is supplied with the control input with the true power load circuit control with the control input AC The block diagram symbol of the magnetic amplifier shown in figure 341. The triangle is the general symbol of the amplifier. The saturated core reactor symbol for the center of the triangle identified with the amplifier. Magnetic amplifier. Note for the input-output signal shown. The input signal is in small amplitude, low power AC signal. Output signal is pulsating DC with the amplitude with the variation controlled by the input signal represents a power gain of 1,000. 341 show the magnetic amplifier input signal at 1 volt and 100 milliwatts. And then an output signal varies with 10 volts and 500 watts. Some magnetic amplifiers designed to the AC go through the load rather than pulsating DC. This is done by placing the load different in circuit with the position with respect to the rectifier. The principle of the magnetic amplifier remains the same. Control circuits still control load currents. The magnetic amplifier provides accurate control large amounts of power. They are used with a servo system, which are covered later in the training series. Temperature of the pressure indicator of the power supplies. Alright, the chapter is presented only with basic operating theory of the saturated coil reactor's magnetic amplifier. For the convenience of simple schematic diagrams have been used to illustrate the material with a magnetic amplifier saturatable coil reactors are used. The actual equipment of the schematic may be more complex than those seen here. As you find the coils, you've the addition of those presented with the chapter technical manual for the equipment in this case should be contained with the information you need to supplement what you have read in this chapter. Alright, chapter 3 summary.